and then I will share my screen and I will move to Maple and you can see how that goes. Okay. So here I am starting an averaging calculation for oscillations. This is the general form of my differential equation. It is a small perturbation of a harmonic oscillator. Okay. And then as I have explained, x and x dot, I'm writing it as a sine t plus phi, and the time derivative of that holding a and phi constant. That means a cos t plus phi. Okay. So think of it as a change of variables. Now, if this is x and this is x dot, then the time derivative of this should be equal to that. So here is the time derivative. And from that I subtract this. So that has to be 0. This is E1. E1 has to be 0. The other thing is the time derivative of x dot, which is here, time derivative with respect to a times a dot, time derivative with respect to phi times phi dot, plus the derivative with respect to time, partial derivative, plus x, so plus x, minus epsilon f, minus epsilon f. This has to be 0 also. Okay. Now this E1 and E2 have to be solved for a dot and phi dot. I'm just calling this set of two equations slow. These are slow equations. Why? Because a dot is order epsilon, phi dot is order epsilon. So this system is now in Lagrange standard form. Once it is in Lagrange standard form, I can do averaging, and I am doing this averaging for the special case. I think I have made a mistake here. This f is minus. Okay, why? Because I have moved it to the other side. Minus x dot times x square minus 1. That's the van der Waals oscillator. When I substitute this f into here, basically I'm substituting here and here. Okay, so I've got that now. And just averaging is straightforward, you see. So I do the averaging. I write a dot average. So what I do is I substitute slow van der Waals into a dot. That means I just pull out this term and then I integrate from 0 to 2 pi. Actually the period is pi because this is also cos squared and sine squared. The period is pi, but it's good enough. 2 pi is also fine. So I integrate from 0 to 2 pi and divide by 2 pi. Okay, so that is a dot average. And then phi dot average, similarly I pull out phi dot and average, and then phi dot is 0. So this is the averaged van der Waals equation. Okay, in terms of amplitude and phase. Does anyone have a doubt about this so far? You have to hurry. We can't record video while you wait to hesitate to speak and I wait for you to speak. Makes no sense. Does anyone have a doubt so far?
No, sir.
All right, thank you. So then what we will do is we will go to MATLAB and see how that works out. Okay, so this is our equation. What is it for small a? For small a, it is a by 2 times epsilon, you see. So a grows exponentially. You can see that. For very large a square is much bigger than 4. And so it is basically minus a cube epsilon by 8. So it decreases very fast. Where are the equilibria? One is at a is equal to 0 and then a plus minus 2. Okay, those are the equilibria. So you can see that there is a limit cycle of amplitude 2, but more than that, we now have a dot. A dot has this epsilon in there. That's okay. That's fine. No problem. We like that. Okay, so we come here and we let's take this equation. Well, no, maybe we will take this equation. So AVG1, who cares? I'll do a new one. Okay. Function x q dot is equal to VDP average TQ. Okay. Then I will say X equals Q1, X dot equals Q2, amplitude equals Q3. I'll solve all equations together. I will say epsilon equals 0.1. That is a sufficiently small number for this problem. Then I will say Q dot is equal to, what do I write? X dot. Then I say minus X minus epsilon times X dot times X square minus 1. Are you happy with that so far? Come on.
Yes, sir.
Yes, sir.
And then here, this one. That's my averaged equation. Okay. Save. Now I will come here and I will say OP equals. Then I will say TQ equals ODE45. Excuse me. VDPAV, which is also vada pav actually, come to think of it, but in our case it is not. Okay. And the initial condition I will take for X, I will take 0.1. For X dot, I will take 0. And amplitude, I will also take 0.1. Okay. All right. So now I will have plot T, Q, 1 and 3. That means I'm plotting X, the oscillatory solution, and the averaged amplitude. And you will see that we have a really good match. Okay, you can see how the amplitude is just being tracked by the averaged equation. It seems that I should go for a longer time, like 120. And you can see that it is settling down. It sort of tracks the whole behavior. How many of you have not seen this averaging calculation before? Many, I hope. Can you raise your hands? Yeah,
Yes,
so
sir.
many of you have not seen such an averaging calculation before. And for you, I hope that this was a nice moment. It's quite surprising how well it works. Okay, many others have not raised their hands. Maybe they have seen averaging before, doesn't matter. Okay, so let's go back to this equation here. Let us try a different initial condition. Okay, you can lower your hands, please. So here we will go now. What we will do is we'll try a different initial condition like 5. And this time maybe only 30, 40 is needed. You see it sort of tracks the amplitude again. Okay, so this is success of averaging. But now let me point out something to you. The rate of change of phase up to first order is 0. Actually, it is possible to do a higher order averaging, which I will do later in the semester, very soon. And in that case, we will get a phi dot average also. It will be order epsilon square. In fact, the A dot average, the order epsilon square term will be seen to be 0, which is why the first order average equation works so well, because actually the second order term is 0. So the error is only third order in epsilon. Okay, so that's one thing. Let's see, what else did I want to say? Why is A dot independent of phi? A dot is independent of phi because the system is autonomous. This system F, you see, it is autonomous. It is here. There is no explicit external forcing. Because there is no external forcing, for this reason, the rate of change of amplitude, you know, where we are saying amplitude is changing very slowly over a long period of time. Professor Steve Strogatz gave an extreme example. He says you think of a little boy's height, you know, the top of his head, right? So there is a long, slow change where he's growing taller, but there is also a very small oscillation due to his heartbeat, right? So if you think of the time scale separation, the oscillations are supposed to be very slow. I'm sorry, very fast, and the rate of change of amplitude and phase is supposed to be very slow. Okay, so for example, if I come here and I make epsilon equals 0.01, and then I increase this to maybe 300, it gets better. I hope you see that it is getting better. In fact, as the time scale separation gets bigger and bigger and bigger, the averaged equations work better and better and better because they are asymptotic methods. Okay, I hope that much is clear. I hope it is clear that in such a situation, if you look at this situation here, the rate of change of amplitude is actually not dependent on the phase of the oscillation. It is just dependent on the amplitude at that time, over a couple of cycles, whatever the amplitude is. It depends only on that, right? So I can go 0, 1. I'm sorry to bore you with this, but there is a point I'm trying to make. This is so now you see you can't even tell the oscillations apart, right? On this time scale. And when you look, it is reasonable to talk about the amplitude at this time. It is about 2.95, So the amplitude changes very little over several oscillations. Okay. Can I stop with the averaging of the van der Pol equation and move to a different equation? Do I have to have a designated speaker, or will someone say yes?
Yes, sir, you can move forward.
Yes, sir.
All right. So let us now. I don't have to restart. What I will do is I will just go back. Well, after all, there is video. There's no problem. What I want to do now is I want to do the forced van der Pol oscillator. Forced Duffing equation. Okay. So for the forced Duffing, I don't want to do amplitude and phase. For the forced Duffing, I want to do this. I want to have a sine term and I want to have a cosine term. This is also reasonable. See, for some f, it's reasonable. Let me show you how it works out for the van der Pol oscillator first. You're seeing I'm doing really nothing different. Okay. This, we are still doing van der Pol oscillator. There's no problem. I have A dot and B dot like this. I hope you see that such averaging is also possible. There's no difficulty. Is that okay?
Yes.
All right. Now what we will do is we will do the Duffing oscillator. So for the Duffing oscillator, what will happen is we will have a minus C times X dot minus A times X cube, right? But also I will have a plus delta times XS. Remember, because I did a detuning. Do you remember?
Yes,
I
sir.
have done it in a
No, sir.
lecture for the Duffing oscillator where I did a perturbation solution. I said let omega be 1 plus epsilon delta, where omega is the forcing term. So when I shift the time, this is it's like increasing the forcing frequency is the same as decreasing the linear frequency of the system. That is why this plus delta, because on the left side it would be minus. Is that okay? Plus f times sine of t. Are you surprised by this, or do you understand this? Who does not understand what I have done here? Who understands what I have done here? Only 2 people have raised hands. What about the others? 4 have raised hands. So it's clear, right? 5 have raised hands and so on. 6 have raised hands. Good. So you can stop raising your hands, but you can look here again. Let me point out that this F is going to be multiplied by epsilon. This thing will go over to the left hand side and become plus C x, epsilon C x dot, small damping, plus epsilon A x cube, small nonlinearity, minus epsilon delta x. So that means the natural frequency of the oscillator is slightly less than 1, plus f sine t. Okay, good. So I should not call it slow VDP now. I'll call it slow Duffing. Then of course I have to come here and say slow Duffing, and I have to come here and say slow Duffing, and let us see what the equations look like. Okay, so I'll just run the thing again. And you see, these are very similar looking equations, right? So what happened is, these are the things that were 0 or something very close, or exactly this was 0 when we looked at the periodic solution. That is because for a periodic solution, A dot has to be 0, B dot has to be 0. A and B have to be constant. But suppose they are not 0, then this is how the solution evolves. Is this part clear to you?
Yes, sir.
Yes, sir.
Okay, so what we are saying is, suppose I have this harmonic oscillator, I release it from some initial condition, then the solution is approximately A sine t plus B cos t, because this is small. If it was 0, the solution would be exactly A sine t plus B cos t for A and B constants. Because epsilon is not 0, it is still A sine t plus B cos t, with A and B varying with time but slowly. The variation of A and B with time has an average part which is slow plus an oscillatory part which is fast. The oscillatory part will be averaged and removed, and then the average part of A and B are changing like this. Clear so far?
Yes, sir.
Yes, सौरभ शर्मा आ कहां से रहे? पहले थे या नहीं थे? Saurabh Sharma, are you just joining us? Okay, so let us look at this now. I will do one thing. Now you see, I am interested in A and B and how they vary, right? This epsilon and this 1 by 8 is only changing the time scale. Do you understand?
Yes, sir.
Yes,
The
sir.
trajectories are the same. So when I look at a phase portrait, I can remove that epsilon by 1 by epsilon by 8. It doesn't matter. Only these are the things that are important. Is that all right? Come on, hurry up, please.
Yes, sir.
All right, very good. So now let's look here and let us look at Duffing. Let's make a new one and say function q dot is equal to Duffing average dq. Let us say A equals q1, B equals q2. That epsilon by 8 I am not keeping. Okay, it doesn't matter because we'll do a phase portrait of this. All right. And then what else will we do? We have to do parameters.
Okay, sir. What does that epsilon by 8 represent?
It doesn't represent anything. It is actually part of the rate at which things vary.
Okay.
The rate of change of A dot is this
Proportional
thing
to epsilon.
times -1 times epsilon by 8. So if I take epsilon to be 10 to the power -5, then epsilon by 8 is almost 10 to the power -6. After 1 million units of time, it will change. by 1. But if I don't keep it, then after 1 unit of time, it will change by 1, but the trajectory in the phase portrait will be exactly the same. That is because I am removing the same from both. If I remove it from here and keep it here, then it won't be the same, right?
Okay.
Because I am removing the same factor from both,
Yes,
both
sir.
are evolving just a little bit faster in time, but their proportional changes are the same.
Yes,
Or
sir.
in proportion, their changes are the same. Is that clear?
Yes, sir.
Good. So here we are. I have to give parameters. Let me say C equals 0.3. Let me say F equals 2. Let me say A equals 0.7. Let me say delta equals -4. So what am I doing? Delta equals -4 means the actual frequency is very low, because remember the forcing frequency is 1 plus epsilon delta. That means I am on the left side of the backbone. Is this clear?
Yes.
This 1 by 8 epsilon I will remove. That's A dot. Okay. Now I'll pick up B dot, and that is just this. This is the averaged equation for the forced Duffing oscillator, weakly nonlinear, weakly forced, weakly damped. Okay, near resonance. Okay, now what I will do is I have to start. I'll start now. I don't have to have such a long time. 20 is more than enough. I have to give it some initial condition. Let me give it 3 and 0 or something, doesn't matter. Okay, all right. Now that didn't work. This is because I am supposed to say Duffing average. Okay, now what I will do is I will plot Q1, Q2. This is basically A versus B. And you see that it is settling down to this solution. Remember, this is the A axis, this is the B axis. Vertical is B. You can see that B is 0 and A is not 0. Positive. What does this mean? It means that over here, the forcing is sine t. The solution is A sine t plus B cos t, but B is 0. Because B is 0, and A is positive, that means the response is basically, the steady state response is in phase with the forcing. Clear so far?
Yes, sir.
All right. Now let me do something else. If you do the time series,
In phase and A is varying also.
A and B are varying, they are going round and round, but finally it is settling down to an equilibrium here. The steady equilibrium here, you see B is very small, A is large.
Yes, sir.
This means that the response is basically in phase. Okay.
Yes, sir.
Okay, this is because it is on the left side. See, I had done this whole discussion for the single degree of freedom linear system. I drew a hump near resonance. Then I pointed out that due to nonlinearity, that hump bends over, you get multi-valued solutions. But on the left side, for low frequency, you just have one solution. For sufficiently high frequency, you again have only one solution, right? And then on the left side of at the very tip, the phase is pi by 2. You see, it becomes a cosine, right? Minus pi by 2 rather. At the very tip, we expect B to be big, but otherwise we expect A to be positive, single solution, single steady state solution. These are the transients. I can show you these transients also in the following way. Okay, so let me show you these transients now. You have seen this transient, right? We are seeing an amplitude of about 3 slowly going down. If I do axis image, you will see that it's almost a perfect spiral, symmetrical. So if I make a time series solution, what will I get? I will find that the amplitude is just slowly going in. What is the amplitude of the solution? The amplitude of the solution is square root of a square plus b square, right? So if I do plot e square root of q1 square plus q2 square, this is the time series of the amplitude. You see, and what the amplitude is doing is it is showing some oscillation and settling at 0.5. So if I start it at a large amplitude, if I start the solution at a large amplitude and the forcing is slower than the resonance, then the amplitude will oscillate until it settles down to a unique steady value. The amplitude will not steadily come down. Why is that? Because the oscillator has its own frequency, which is 1, and the forcing frequency is a little bit less in original time, right? So as a result, some beating will occur. How many of you believe that this oscillatory behavior is real? That it really will be seen?
No, sir.
You don't believe, right?
Yes, sir.
Okay. Who else is skeptical that averaging has given a meaningful answer? Everyone else believes?
No, sir.
Okay, how many don't believe? Let's see hands. How many think that this needs to be investigated? This is very funny. This oscillating amplitude. How many of you think that the oscillating amplitude at least needs to be verified? Let us not waste time. Ratnang Shudas wants to verify, Vishesh Kaushik, so many other people. So you want to verify whether this oscillating amplitude is real. Very good. Let us verify. Okay. So we will share screen. You can lower your hands, please. And we will verify this. How will we verify it? It's quite easy, not a problem. What we will do is we will make a new file. Q dot is equal to f duff tq. Okay, so this is the original one. I will say epsilon is equal to 0.01. Okay, so epsilon is quite small. I will say q dot is equal to q of 2, and then the q dot of 2 is equal to minus. So I have to specify parameters that I will specify from here. Okay, then I will say minus, wait, let me do this. X equals Q1, V equals Q2. I hope you don't mind. This will simplify things. Over here, I'll write V. Then over here, I'll write minus X, right? Because this is, I'm doing it in original time. Okay, minus epsilon times C times V minus A times X cube plus, this has to be epsilon, plus epsilon times F times sine of 1 plus epsilon times delta times T. Do you agree that I have written the correct equation?
Yes,
Yes?
sir.
Yes, sir.
All of you agree? Can I have a chorus of voices, please?
Yes, sir.
Yes, sir.
Yes, sir.
Very
Yes,
good.
sir.
Yes, sir.
Very good. Now, what was the time to which I had done the integration earlier? I will see that here very easily. I had done till
20.
20. So now I have to do till 2000. No, actually epsilon by 8. I may have to do till 16,000. Okay, fine. We'll do something. I'll do 8,000 and we'll see. I don't need that much. I only need about 4,000. Okay, so I will do that. I'll do up to about 4,000. What is the initial condition that I should use? I'll just use an amplitude of 3. Is that okay?
Yes, sir.
Then we'll see the solution.
Yes, sir.
I don't want that. I want F Duff. Ready?
Yes, sir.
All right. So you see the oscillation is real. When you come in here, I have done only a small part of that total time. So it is oscillatory. It is oscillatory, but the amplitude is changing, right? So the oscillation is real. There's no question. And it settles down to some value. And if you look there, you will see that the amplitude is, something seems to be a bit off because this amplitude is 0.25. I don't know why that is.
Yes.
Why is that? It should match better. Oh, but it will match if epsilon is smaller. Okay, so let me make it 0.2. And let me make this 12,000. Minus x minus epsilon. Oh, wait, there is a problem. There is a problem. I will tell you what the problem is. In a minute, I will tell you what the problem is. Okay, but let me see how this one works. So it has not yet settled down, but it will settle down to some slightly different value, still coming to about 0.25. Okay, the reason is I am doing this equation in a slightly different way. Let me not do that. Let me say minus x minus epsilon times delta times x, and let me just do t. This is exactly the equation we have averaged. Correct?
Yes, sir.
Is it minus or plus? This is plus, so that would have been minus on that side, yes? So on this side, it should be plus. So I will make this plus. This is exactly the equation we have averaged, okay? Let us not get confused about what equation came from where. So now it is going more slowly, but you will see that the oscillations will probably settle to a more meaningful value. I don't have to use this very small value now. I made epsilon 0.01 again. Okay, I hope you will agree that this match is better. Okay. You see it is 0.45 or so, whatever that average was.
Yes,
right?
sir.
Okay. What I will do is I will say hold on. Now I will come here and I will say Q dot is equal to Q dot times 0.01 by 8 to put it back to its old value, to the correct value. You understand? Because I had epsilon by 8 previously. Okay. And this initial condition where x is 3 and x dot is 0 corresponds to b equal to 3 and a equal to 0. I hope you understand.
Epsilon you changed.
Sorry?
Epsilon you changed.
Yes, I put epsilon at 0.01.
Okay.
Therefore, over here, I am doing 0.01 by 8. I will compare directly, no? Okay. So now for the average, remember for the time domain equation, what I have done is I have taken x equal to 3 and x dot equal to 0. When I write x as a sine t plus b cos t, this means a is equal to 0 and b is equal to 3. Yes?
Yes, sir.
Okay. So I will come here and I'll say Duffing average. And then over here, I will use 0 and 3. And I have another solution. Okay. And then I will do amplitude is equal to square root of Q1 square plus Q2 square. And then I will say plot T amplitude in red. Okay. Let us see how it works. So you see that is the averaged equation. I hope you will agree that it is very good. If you do second order averaging, the match will be better. There is a slight difference in, the phase of that oscillation in the amplitude because we are doing only first order averaging. But if you look at this part, you will agree that the match is extremely good.
Yes, sir.
Okay, so averaging is right. These are asymptotic methods. If I make epsilon smaller, it will be even better. It won't be worse. So is everyone convinced about the result at least so far?
Yes, sir.
Yes, sir.
Okay. Now let us put delta equal to 0.
Okay.
When I put delta equal to 0, not much will change. So once again, now wait, I'm going to remove this now so that I can do faster simulations. Now I will do only 20. And I will do plot Q1 versus Q2. So you see, once again, it has come in some way, it is spiraling in, but there is maybe something funny over here. That is all. Okay. So what I will do now is I will say, hold on. Then I will say for k equals 1, 2. Well, that didn't work. Okay. So for k 1 to 10, x is equal to g input. Then what I will do is I will run it for 20 time units with that initial condition and Duffing average, and then I will plot. Okay. So then I'll get a phase portrait. Clear? I have done this before.
Yes, sir.
Okay. So here I will get a new phase portrait now. You will see basically nothing, no surprises. Still just one unique solution, periodic solution. And still you will see that A is much bigger than B. The amplitude is bigger. Why? Because I am getting closer to resonance. So the amplitude is now a little more than 1.5 and a small cosine component is there. Right? The cosine component is 1/5 of the sine component. But there is a lag. Okay. So this one we have done now. How about delta equal to 1? When I do delta equal to 1, let me start.
Sir, ideally at delta equal to 0, cosine component should have been absent.
No, it is only an approximation. There is damping over here, there is nonlinearity. Right? I said that on the left side, it is essentially in phase. A small phase difference is there because there is damping. If there is no phase difference, then there will be no dissipation. Right? Because the force is sine t. If the displacement is sine t, then velocity is cos t.
Yes, sir.
Force into velocity is sine t into cos t. Its average value is 0.
0.
It is because of dissipation that some cosine must appear in the velocity, so that in the displacement, so that sine will appear in velocity. Clear? Okay. So here this is for delta equal to 1. Now I will do hold on, and then I will do another phase portrait. And you see still there is nothing, no real change. You can see something is going to happen over here, right? But we don't see what that is yet. What will happen is that there will be this bifurcation and two new solutions have to appear as delta increases. And both of them will correspond to negative A.
So means that the change for bifurcation has begun.
The shadow of that is here, although the bifurcation hasn't occurred yet. Right? The shadow of it is here. So let me explain with a drawing. Sorry, maybe like this. Okay. So we are doing a perturbation study. So we are in this region only. But over here also, for large negative delta, amplitude is small. For small zero delta, amplitude is bigger. Still bigger delta, amplitude is still bigger. Then still bigger delta, what happens is two new solutions appear. This one remains stable, but over here two solutions appear. I have claimed that this will be stable and this will be unstable. That is what we want to see now. Okay. Over here, largely in phase. Over here, largely out of phase. Therefore, both of these, A less than 0, B small. That is what we expect. Okay. All right, let's return to our MATLAB here and let us make delta equal to 4. If I do a continuation solution of that, I'll know the exact value of delta, but I'm not doing that here, okay? Okay, now some other funny things have happened and we will try to see what the story is. And so what we will do is we'll do axis minus 5, 5, minus 5, 5. We'll do axis equal. Okay, and then we will do hold on, and then we will do for this, and we will come here. And you see here is this large amplitude solution just filters down and comes to this large amplitude solution here. But there is another stable solution here. You see two stable solutions. Both of these, the B part is relatively smaller. For this, it is particularly small. But over here also, it's relatively small. That is 1.2 and this is 2.4 or something. Or 2.8. Okay. But where is the third solution?
Yes, sir.
Okay, the third solution is here and it is unstable. So you see, that's where the third solution is. That's where the third solution is. You see, there is a saddle there.
Yes, sir.
Okay, so there is a third solution here that is unstable. There is a stable solution, right? And this
The
is
saddle is we cannot say about saddle is stable or unstable.
saddle is unstable. One eigenvalue is positive, one eigenvalue is negative. Both are
Yes,
real.
sir. Yes, sir. So
It is
it's
definitely unstable,
okay.
right? In fact, this thing is called a saddle node bifurcation. One stable, one unstable, but turning point bifurcation. So because of that turning point here in this figure, there is a turning point. Okay. And then there is now, beyond this, there is not that much. Okay. So that's what the phase portrait looks like. What I want you to understand is, let's see, maybe I'll do it in a little while, but even here it can be done. You see, you look at this solution. You look at this yellow solution that went in, right? This yellow solution came from here. Let's do a few more. Then you will see what I'm doing. See, you see this solution, where did it go? It went to the small amplitude solution, right? Did you see this solution? This one just went, it went here. Did you see that? I will
It
do
went
it
to the
again.
large amplitude when the previously which you drew.
But this one is going to the small amplitude solution. There you
Okay.
see. But then if I come here, this went to the large amplitude solution.
Hmm.
Then if I come here, large amplitude. But if I come here, small amplitude. So even from, there are people in some older books, there are people who draw this picture and it is wrong. They say this one is stable, so this one goes like this and this one comes like this. They say this. That is wrong. From the high amplitude, there are solutions that will come to the low amplitude, and there are other solutions that will come here. They will simply not come here. That is all. Is this part clear?
Yes,
I have
sir.
shown you in this. If you do the time domain simulation, it will match. You know exactly it may not match. So if you have some initial condition here going here, you may have to choose a slightly different initial condition before it will match the numerical solution. That's a different matter. But qualitatively, there is no doubt that this is what will happen. Okay, this unstable solution, this stable solution. Now, if I increase delta, what is expected is that the unstable solution and the stable solution will merge and disappear. Okay, so over here, if I increase delta, that means I go like this, the stable solution and the unstable solution will merge and disappear. This stable solution will persist. This is what I have told you before, right? I'm showing you that now. So here we are. What do we expect? We expect this unstable solution and this stable solution to merge and disappear. Where will they merge? They will merge at this point where the solution is essentially cosine. That means they will come here and merge on this axis. A will be nearly 0 and B will be not 0. Okay, let us verify. So here I will now put delta equals 8. I don't know whether that is good enough. It might be too much. We will see. See, now there is only one solution. So it may be, maybe I should use a larger value. Some issue is there, but over here we are not seeing anything. Maybe I will use
7.
6. Okay, so I hope we will see this is still here. 7. Who said 7? We'll try 7.
7.
Okay, let's try this and see what happens. Okay, so here we have one, here we have another, here we have another, and another. The saddle is still very much present. This saddle and this, they have not yet come close. If I use axis image, I'll get a better idea. Axis equal, I'll get a better idea. So the saddle is now somewhere here and this is still here. They have come, but they have to come closer. Okay, so then maybe 8 or 9 was appropriate. I just left it early. This is still very much there. And this saddle is also very much there.
Yes, sir.
Okay.
Yes, sir.
If I use axis equal and make it bigger, you will see that it is coming closer. They are coming closer. That means maybe I have to use a very large value. Okay, so I'll use a very large value. You can do, it is 311. I don't have too much time, but where do you think it might be? Let's try
16.
Okay. Only the small amplitude solution is left. You see, it has disappeared. Something is going on here. I don't know what that is. Here you go. I have to use larger axis. No, that's not what I want. That's what I want. So yours, you know, it is going. The saddle is now, it will come here, you know, the saddle is here somewhere. When we do a more, you can see that they are closer. The angle between them is now only about 40 degrees taken from here, right? Previously, they were more like this. You can see that they will go there and merge. Shall I do a continuation approximation to see where it intersects? Would you like to see that?
Yes, sir.
Okay, so let's do that. Okay, let's do that. So for that, I just have to take these, go to junk, and do that. Now this will be Z, and this will be delta. Clear so far? That's all, nothing else. A and B are there. I have to specify that. So I have to say A equals x1, B equals x2. And then my usual continuation method will work. So I will come here and I will say clear all. I will say global that. I will say alpha is equal to -4 because I saw that there was a clear solution there. I will say Newton junk like this, and I will put something like 0.5 and 0. And I've got an answer. This is what we got in the beginning. I'll say big X equals that. Then I will say alpha is equal to -3.97. And then I will say Newton again. And then I will say big X is equal to that. I've got 2 now. Then I will say continuation, and then I'll do maybe 160 points. Then I'll say plot big X3, which is delta, and square root of the sum of big X1 to 2 square. That's the amplitude. Okay, it is still going. I need to take longer. Let me take 400 just so that I don't have to. Oh, it is still going. Now it has turned around. You can see that it has turned around. Okay.
Yes.
It may seem like these are very close, but we are actually taking many points. So if I plot it like this, you may see that even here we have many points. It is not that we don't have enough points. We are resolving everything. Okay. So 23.3 is where those are very close. 23.35, it's very close. Okay. 23.4, definitely it is finished. Okay. So if I go back here, not this one, this one, 23.5, for example, or 4, there will be nothing there. So if I go like this, now why is that? What am I missing? What was I doing earlier?
So you have written GOP instead of
GOP.
Oh, I see. Don't know what that is. Okay, then I have that. Let's see. Okay, so there it is going there now. Those solutions have just
Disappear.
let us try. You see, so it is doing some funny thing over there, but that solution has disappeared. Those other equilibria are no longer there. I hope you agree that they have disappeared. According to our analysis, they have disappeared. We know these are the same equations. if there is no equilibrium, if there is no equilibrium in this, then there is no equilibrium in this. They are the same, right? Okay, so that's that as far as I'm concerned. I have shown you the averaging calculation. I have shown you the force Duffing, and I have shown you that at least in the weakly nonlinear case, in this type of solution, this is stable, this is unstable, this is stable, averaging and full time simulation match, and there are high amplitude solutions that end here and also the others that go all the way here. Okay, so these are some things I've shown you. I've shown you the amplitude tracking of the van der Waals oscillator is very accurate, right? I've shown you that. What else have I shown you today? Some Maple and MATLAB calculations. As far as I'm concerned, today's meeting is over. I will stop recording.